Ladies and gentlemen, in the last class we said about the full adder block. We designed it and simulated in QUCS, Verilog, etc. Now we are using that full adder block to make a 4-bit parallel adder in this session. So let me start with that presentation. So what you see in this session are first your learning outcomes, then the 4-bit parallel adder and its structure, then the simulation of a parallel adder in QUCS, then the 4-bit parallel adder in Verilog, and we will see the implementation of 4-bit adder with IC 7483, and in the end the summary of your understanding. So what you will learn in this video is that you will learn to realize a 4-bit parallel adder with full adders. Then you will implement this setup in QUCS and Verilog. Then you will appreciate the wiring diagram of the 4-bit full adder, parallel adder using the IC 7483. Now a 4-bit parallel adder looks like this. 4-bit parallel adder is used for adding the numbers, say A3, A2, A1, A0. These are binary numbers, A3, A2, A1, A0. This is a 4-bit number. So it can be anywhere between 0, 0, 0, 0 to 1, 1, 1, 1. So the maximum number is a 15 and the minimum is a 0. And another number, B3, B2, B1, B0. This also can have a pattern from 0, 0, 0 to 1, 1, 1. So this adds this B3, B2, B1, B0 with A3, A2, A1, A0. So we are adding bit by bit. So we need there are 4 bits to add, and we need 4 full adders connected in parallel, because the parallel means this addition is happening in parallel. So A0 gets added with B0, B1, A1 gets added with B1, A2 gets added with B2, A3 gets added with B3. Now along with the carry also. Now if you look at the carry, and the initial carry is a 0, because this is actually a half addition. This stage is a half addition stage. The rightmost bit, it does not have a carry input. So this is either we use a half adder here, or if you are using a full adder, that carry input line is grounded. It is connected to logic 0. Then the carry output of the first stage, that is C0. This is FA0. This is the first full adder, 0th stage. Its output is one is some bit S0, and the output is a carry. So this is connected to the carry input of the second stage, that is FA1, to which A1 and B1 are applied. So this FA1 produces a some S1 and a carry output that is connected to FA2. Okay. So here this adds C1 and B2 and A2. Now the last stage of the full adder, its sum is S2, and the carry output is C2. C2 is given to the last full adder stage, to which B3 and A3 are given. Now its sum is C3, and the carry is sum is S3 and the carry is C3. So the number at the output, or the sum at the output, is the pattern C3, S3, S2, S1, S0. Suppose if I add 15 with 15, suppose this is 1, 1, 1, 1, and this is 1, 1, 1, 1, then this will be like 1, 1, 1, 1, 0. Okay, that makes it a 30. Okay, so C3 is also part of the sum. That is a point. C3, S2, S3, S2, S1, S0 is the sum. Now, what we do is we have to build blocks. In the last last presentation, we understood how to make a full adder block. So we can put 4 such full adders, and we can connect them together. So I will show you that thing. So this is a QUCS block for a full adder. This is a QUCS block for a full adder. So what I can do is this block, this is a sum output and this is a carry output. These are the bits A0 and B0, and this is a carry in. This may be grounded, may be connected to logic 0. This is a sum output of that stage S0, and this is a carry output of the first stage, that is connected to the carry input of the second stage. Here other bits B1 and A1 are applied. Sum is S1, and its carry is C1. C1 is connected to the next stage, that is a carry input of the next stage. So that carry propagation happens this way. So if I look here, this is my third stage of full adder. Here I have B2 and A1, A2 are added with C1. Okay, so this generates a sum S2, and its carry is propagated to the next stage. Here it is connected to the carry input of the last stage. Here I apply A3 and B3. I get this is my S3, this is my S3, and this is my C out. So C3, S3, S2, S1, S0 is my sum. Now I will show you a demo of this in QUCS. If you look into this circuit, this is such a circuit. This block is a 4-bit parallel adder. If I go into the subcircuit of this one, you can see that it is you go into the subcircuit. Now you can see that I have I have this block. These are full adders. If I go into the one block of this, you can see that it's a full adder block. This is one full adder block. I can go inside that. You can see that it's a full adder block. Okay, this is a full adder block. Okay, so this full adder I used to create. I make 4 instances of this full adder. Okay, I make 4 instances of this full adder. Here these 3 are my inputs for each full adder. These 3 are my inputs. These are my input bits, and this is my carry input. Okay, and this is my sum output. This is my carry output. This carry output is connected to the next carry input of the next stage. Okay, here I apply input and output ports, so to make it a sub-circuit. So here this is my second sum. Okay, this is my second carry, that is, this is my C1. Okay, C1 is connected to the carry input of the next stage, This gives me S2, the sum, and here in the last stage, this is my carry C2. C2 is given to the carry input of the last stage. Here this is my last sum, and this is my last carry. Here I marked as S4. It's actually the output of last carry. So this S4, S3, S2, S1, S0 gives me the sum. Now this being my sub-circuit, I put it in a block. So conveniently I put it in a block, and I apply these signals. Say this is my B0, B1, B2, B3. These are my one binary number, B3, B2, B1, B0. And here I give the second number A0, A1, A3, A2, A1, A0. This is my second number. And this is my S4, S3, S3, S2, S1, S0. This gives me my sum. Okay, this is very compact. Now what I did is first I made a circuit for a full adder with a XOR gate, AND gate, and OR gate. Then I made it into a block. Then that's a full adder block. I tested that. Then I make 3 instances of that full adder. I connect the outgoing carry to the incoming carries of the left stage that way. Then I make a block of that. It becomes a 4-bit adder. So that block is here. I use this. I'll be using this block for other purposes also, like BCD adder, etc. Now let me run the simulation. Now here in these subcircuits I don't have any simulation block or sources or source or anything, but here I have a simulation block, sources, etc. Now I run the simulation. You can see that it is performing the addition. Suppose I look here, it is 1010. One number is 1010, it is 10. And the second number is 0001, it's a 1, so the number sum should be 11. It is 01011, that is 11. Or you can take arbitrarily any case. Suppose here you say it is 1010, that's a 10. Here it is a 1000, it's a 12. So the result should be a 22. So here it is 1010, this is 1100, that's a 12 plus 10, that's a 22. So it is a, you can see that it's a 1011 is 11, added 0 it becomes a 22. 101100 is a 22. Or if I look here, it is 1011, that is 11 plus 8, okay, that becomes 19. It is 10011. Okay, 100, 10 is 18, 10011 is 19. Or here it is, I have 1011, that is 1010, that is 11. Okay, this is 1101, that is 13. So the result should be 24. 24 is nothing but 1100 is 12, 11000 is 24. Okay, so you can build such circuits, and you can verify them to your heart's content. So this is how I do the simulation in QUCS. Now, how do I realize such a thing in Verilog? How do I realize such a thing in Verilog? So first of all, I have made a full adder block earlier, or full adder v.v file or Verilog module. So first that I have to include that is a grave include fadder.v. Okay, so this the module fadder.v is included. This is very similar to the QUCS. I make a one full adder, then I make 4 instances of that. So here I start with a keyword module 4-bit adder, some name 4-bit adder, output wire here. Otherwise I will go to that code and explain to you. It will be easier here. It's a 4-bit adder.v. If you look here, you can see that first it's a grave include fadder.v. fadder.v you have already seen in the last class. I wrote a Verilog module for a full adder, 1-bit full adder. Now there's a module 4-bit adder, output wire 3 is to 0, that is 3 down to 0 means I realize it as a bus. Some is put as a vector, like there are 4 values. It's a 4-bit pattern. It's a 4-bit pattern rather than working out bits individually. I assume that this sum is a 4-bit number, so that is why I write 3 down to 0 sum. Then output is wire C out. Then input lines X and Y, they are 3 down to 0. Okay, they are 3 down to 0. And the wire, and this is my declaration. Now there are some local nets that may be wire C in. C in is an input. This is my first the carry input to the rightmost stage that I kept at 0. That's always logic 0. Then I have some internal wires, that is C0, C1, C2. Okay, now I make 4 instances of the full adder, just like I put 4 blocks in the QUCS diagram. I make 4 instances of the full adder, that is f adder, say f0. Okay, then here what this computes is, it takes x0, the input x0 y0, that is the first bits x0 y0, and the c in, which is held at 0, and produces a sum 0 and carry output C0. So this is the first full adder block. It is taking the first bit or LSB of x0 y0, and it adds with a 0, which is C in, which is a 0, and it produces a first sum bit, sum of 0, and the carry C0. Now this carry is given to the next full adder. So f adder full adder f1, say some name. So that input is x1 and y1, that is the second bit, x0, x1 and y1, and the carry from the previous stage, that is C0, is also added here. So this produces the first bit of the sum, that is sum 1, and outgoing carry, that is a C1. Now this C1 goes into the next full adder, that is f adder fa2, say. That is it takes in the values x2, y2 and the previous carry C1, and produces the second bit of the sum 2, or rather the third bit, sum 2, and the outgoing carry C2. Now this C2 is propagated to the next full adder, that is fa3, that adds x3, y3 and C2, and it produces my last output carry C out. Output carry C out and sum 3. Now C out, sum 3, sum 2, sum 1, sum 0 is my final sum at the output. Okay. Now I can write a test bench for this. It's pretty straightforward. It's a 4-bit adder TB. Now what I do is here it's a 4. I have to include the 4-bit adder.b. Then these signals are to be given just like I gave in the other one. And here I have to give these signals. Here the only difference is I give some randomly. I give some signals. Only thing is X is a 4-bit pattern. B000, 4-bit pattern B001. You can add more of this, like I can have. Okay, so these are the excitations I have to give. Now I will run these codes, both the unit under test as well as the test bench. I will enhance it a little. Now this 4-bit adder is compiled without any problem. Now what I do is full adder TB with some output file, say -o a dot out. Now I can run this a dot out. Now we can see the sums happening at 10 second. You can see that the input X is 0000, Y is 0000, carry out is 0 and sum is 0. All is a 0 pattern. Now here I am adding 100 with a 0, that is 8 plus 0. What you get is 0100, which is 8. Now here I am adding 12 with 9, that must be 21. Okay, here I am getting is 10101, which is 21. Now here I am adding 1100, that is a 12 plus 13. Okay, that is 25. 12 plus 13 is a 25. So I can see that is 1100, which is 12. Another 0 is 24 plus 1 is 25. 110001 is 25. In the last case it is 15 plus 13. That must be a 28. 28 is nothing but 1110. 11100 is my 28. So you can see that the full adder block is the 4-bit full adder is working correctly. Now you can in your lab you can implement this 4-bit full adder with an MSI chip, a medium scale integration chip, that is called 7483. 7483 is a 4-bit full adder. You can take this 7483 and place it on a breadboard, and you can ground this 12th pin, that's a ground. Okay, you ground this pin, then apply VCC or 5 volt to the pin here. The 5th pin is VCC. Then you can apply these bits like this, like the first number A3, A2, A1, A0. You can give like this, like A3 is here, the first pin. A3, A2 is in the 3rd pin. A3, A2, A1 is in the 7th pin, and A0 is somewhere here, that is in the 10th pin. And B3 is given in the 16th pin. It is a 16-pin chip. B3 is given here. B2 is given in the 4th pin. B1 is given in the 8th pin. B0 is given in the 11th pin. Okay. Now you can see that the sum is given here. S3 is here in 15. S2 is in S2 is somewhere here. You can see that C4 is my 14th pin, S0, S1, S2 is in the second pin, S1 is in the 6th pin, and S0 is in the 9th pin. Now you can connect LEDs to C3, C3, S3, S2, S1, S0, and normally one way through a 220 ohm resistor, and you can connect these A and B numbers to toggle switches. Then you can toggle these switches and apply patterns of your patterns of your liking, and you can verify this output. Some output will be my C4, S3, S2, S1, S0. That will be your sum. So you can verify in the lab. First you check the 7483 on a IC tester and place it on the board, ground the ground pin first, then connect the supply, connect all these things like this wiring diagram, and appreciate the results. Of course, the C0 should be connected to logic 0. I forgot to say that. There's a carry input terminal, that is C0. C0 is here. This should be connected to logic 0. That is the incoming thing. This pin is available there because you can cascade this further. This is a 4-bit adder. You can make it an 8-bit by connecting one more stage, and the carry output of the first stage can be connected into this pin, so that that works as a 4-bit 8-bit adder. You can play around with this in the lab. Now when you come to the end of this, what you understood here is you learn to realize a 4-bit parallel adder with full adders. Then you implemented this in QUCS and Verilog. Then you appreciated the wiring diagram of the 4-bit parallel adders IC7483. And that is the end of this presentation. I thank you all.